What's up everyone? Today we're going to go over Leetcode 994 rotting oranges. Now I made a video for this before, but I'm remaking it. So the input is going to be a 2D grid of integers filled with the zeros, ones, and twos, and the output needs to be an integer. So zeros represent a empty space, 1 represents a fresh orange, and 2 represents a rotten orange. So I've color coded that. We have 0 for empty, 1 for the orange color, and 2 for the red color, which is a rotten orange. So what the question is asking is how long will it take globally for all the fresh oranges to become rotten? In other words, the oranges have to become red. So let's look at how that happens. Now, every minute, a rotten orange is going to rot the adjacent oranges up, down, left, and right, and change that into a 2. So at the end of the first minute, this orange is going to rot the adjacent oranges. At the second minute, these oranges are going to rot those oranges. In the third minute, this orange is going to rot this orange. And in the fourth minute, this orange is going to rot this orange. So this connected component is going to take 4 minutes to rot. Let's look at this connected component. This orange is going to rot its adjacent orange after 1 minute. This orange is going to rot its neighbor after 2 minutes. What the question is asking is how long does it take globally for all the connected components to finish rotting? So because this one takes 4 minutes, this is going to be the output. Now this connected component is going to finish rotting before this one. Now there is one edge case where it says how long will it take for all the oranges to rot, right? But there is one edge case where if there is a connected component, whether that's one orange or multiple oranges, which will remain fresh after all the rotting is done, then we have to return -1. So in that case, the output would actually be -1. So let's look at the intuition and how we're going to keep track of this in the next segment. Okay, so let's look at how the rotting happens at a closer level. So we know that if we have a rotten orange and these are the adjacent oranges, the rotting would happen as so. After 1 minute, this rots. The second minute, and the third minute. In other words, this is nothing but the distance of a given orange from its closest rotten orange. So anytime we're talking about distances from a origin to a destination, we know that it will be a BFS approach where it's more layer focused. So how can we keep track of these layers? Well, either we can tell a orange that's adjacent to a rotten orange, hey, I'm 1 minute more rotten, or rather I should say, it takes 1 more minute for me to rot than it takes for you to rot. So in the beginning, it takes 0 minutes for this rotten orange to rot because it's already rotten. This one is going to look at its rotten neighbor and it's going to say, okay, it's going to take me 1 more minute than it took you to rot. Similarly, this is going to be 2 plus 1, and this is going to be, this is going to be 1 plus 1, and this is going to be 2 plus 1. So essentially, the states or the number of layers are being transferred from one node to adjacent node. Now, there's a couple ways we can implement this. I prefer to implement it where the node itself is keeping track of which layer it is. I believe this is a more versatile approach. I will link down below to an implementation where the node itself doesn't have to keep track of the layer, but we'll have to use a sort of delimiter or dummy orange to keep track of the total number of layers. Now keep in mind that we want the global answer, and I'd like to go over a case where there could be 2 rotten oranges in one given connected component. So this question is what I like to call a multi-origin BFS. Why? Because there are more than 1 rotten oranges, right? And they all start rotting at the same time. So we cannot keep the layers at the Q level, meaning we cannot rely on the Q to tell us how many iterations it's had. So it's better, in my opinion, to go ahead where we let the number of minutes that have elapsed be stored in the orange itself. So let's look at another example. All right, so I've written 2 connected components side by side to highlight an important difference. We have to keep in mind that all the oranges start rotting at the same time. It would be incorrect to think that one rotten orange finishes rotting its neighbors and then the other one will start. So let's look at what I mean. Now this is pretty basic, so good so far. So this is incorrect because we didn't take into account that this rotten orange also rots its neighbors. The correct approach is this. So technically, this orange is being rotten by both this one and this one. So the correct answer for this connected component would be 2. The incorrect answer for this connected component would be 3. So let's look at how the code is being run. Okay, so I'm making a small segment just to explain the helper code. So class O represents the orange, and this is what I'm going to put inside my queue to do my BFS. So every orange O is going to have the coordinates, so X and Y, and it's going to contain the layer it is from its closest rotten orange. So this is just 2 integer arrays to help me keep directions up, down, left, and right, because we're constricted by that according to the question's requirements. If we can do all 8 directions, I would just expand this. And this is just a helper method outside. So given a grid and 2 coordinates, I'm just going to return true or false if it's inside or outside. Let's look at the meat of the algorithm. All right, so I've written the meat of the algorithm and I've split it into 3 parts. The first part is loading the queue and getting ready. The second part is the actual searching of the largest layer we can find. And the third part is a search for an edge case. So to begin, all we have to do is iterate through the 2D grid, and anytime we see a 2, which represents a rotten orange, we add it to the queue, and the layer is going to be 0 because the number of minutes it takes for a rotten orange to rot is 0. Then we begin with our max, and this is what we're going to use to call math.max and update it anytime we see a larger layer inside an orange. So the first part, of course, we pull the orange that's at the beginning, and we check right there, hey, does this have a maximum which is greater than my current maximum? If so, we update our max. Otherwise, we use our 2 helper arrays from earlier, and we check up, down, left, or right for a new coordinate, right? So we say row. And then if that row and column is not outside of the grid, and if at that row and column I'm looking at a fresh orange, what I'm going to do is rot it first, and then I'm going to initialize a new orange and put it in the queue. And here's the core part of it, is that I'm going to add 1 plus to the current orange I have. So for cur, if the original thing was 0, I'm going to say 0 plus 1, and that's how we're going to let each orange keep track of its individual layers. And then once we're done with the entire queue, right, once we're done pulling and it's no longer having any more oranges left in it, we're just going to get the maximum. And before we return the maximum, we're going to do 1 edge case check. We just go through the 2D grid and look for any remaining fresh orange. So just a 2D iteration. And if any of this is a 1, we just return -1. Otherwise, if we pass the edge case, then we're going to return the maximum that we've updated and initialized over there. So that's how you solve Leetcode 994. If you liked the video, please thumbs up and subscribe. And always, thanks for watching.